Hi, welcome guys. So previously we already talked about, we just talked about some module, but in this new section, and let's talk about linear transformation. Okay, so start from here should be viewed as a linear algebra second part. Yeah, so so basically I want to prove some fact that seldom people prove in the linear algebra, basically hard to prove, a little bit hard to prove. Okay, so this section I want to talk about the algebra of linear transformation. Okay, so right, so remember that V is vector space over F, and we already talked about how VV is basically all the linear transformation T, right, from TV to BV. Right, so in the previous video that we proved that this is a vector space. Right, this is a vector space, and by defining T1 plus T2 x on V, T equals to T1V plus T2V, and also alpha T1V defined to be alpha T1, sorry, alpha T1V defined to be alpha times T1V. Okay, so these operations make this Hom VV as a vector space, and then we also proved that the dimension V is n. Then if dimension V is n, then Hom VV is a vector space of dimension n squared. Okay, and you might think that so yeah, right, so we finish, right? But not really. Okay, the reason is that one can define a Hom. One can say that given T1 and T2 in the Hom VV, one can operate T1 T. One can consecutive times T1 and T2, right? So this make so easy to see that the definition T1 composite with T2 x on V is defined to be T1 x on T2V. Okay, so sometimes I'm lazy, so I only write these things. Okay, and also you should check by yourself the rules. Basically, if you get T1 T3, you get T1 plus T3 T2. You can separate it into two, right? And also T3 T1, T3 T2, and so this is a rule, right? This is the associativity. Okay, also it's linear in alpha, right? So alpha T1 T2 is alpha T1 times T2, also T1 alpha T2. Okay, so you see this makes what? So makes Hom VV a ring, right? Not commutative, but ring. But you also know that there is identity, right? So it's a ring with identity. Okay. Okay, and you can take the element alpha times T1, right? So basically you have a field F, right? So now we have a field F, and at the vector space Hom VV, and we can define a field X on Hom VV go to Hom VV, right? So you can multiply some constant in an associative ring. Okay, so let me just go a definition. So if you have an associative ring A and called algebra over F, so in this video I only talk about associative ring. Basically I only talk about algebra over field F, right? So but in general you can define in other like a ring or something. So if you have associative ring A, so the A cell must be an associative ring, and it's called algebra over F. If A is a vector space over F. So remember that the Hom VV is already a vector space. A is a vector space over F. Right, such that so A itself is not only a A itself is a ring and also vector space. So it's very various lots of criteria such that if you have AB belongs to A, then you get an alpha belongs to F, such that alpha AB equals to alpha A B A alpha B. Okay, so fact. So from previous that the Hom VV is not just a ring, right? It's not just so it's a vector space. It's also a associative ring. It's also algebra. Okay, so usually people write as AF V if I focus in the algebra side. Okay, so since you know it's algebra, so you can use a lot of things, a lot of technique to deal with such things. Okay, theorem. So this theorem, I want to say that so this theorem is general results. So if A is algebra, over F. So remember, algebra over F means A is associative ring and A is a vector space over F. And then with the unit element, so the unit element required for ring, right? That's identity. And A is isomorphic to so-called subalgebra. Okay, so subalgebra is also algebra, but only talk about subsets. So fact is that A is isomorphic to A of V. Okay, for some vector space V over F. Okay, so this theorem, what I'm saying is that oh, by the way, so this should be AF3. So what I'm saying is that all algebra over F with units looks like some subalgebra. So moving to subalgebra. Look like some subalgebra of the Hom VV for some vector space V. Okay, so this tell you that the algebra with units over field F is basically looks as a subalgebra of the Hom VV. So that means Hom VV contains a powerful representation which should eat all algebra. Okay, yeah. So actually, I didn't. By the way, I didn't define isomorphic in algebra, right? But this is just a sense that you can define a one-to-one linear transformation. Okay, now this should be viewed as if you learn about enough mathematics, this is abstract version of the, I think it's the Cayley's theorem for groups. There's like I should be another version, right? So Cayley's theorem for groups tell you that any finite group, so if G is finite, then G should be viewed as a subgroup of the symmetric group of permutation G. Okay. Proof. Proof should be not difficult, right? So if A belongs to A, you can define a transformation called TA, right? This AA, you define a TAV to be just what? So A belongs to A is algebra, right? So A is algebra, right? So you can define TAV to be AV, where V belongs to A. Okay, so remember now, forget about the linear vector space, right? I'm talking about algebra, right? So you can any two element in algebra can times itself, right? So I define this. Okay, so obviously check by yourself, TD is a linear transformation. Okay, so this is the by definition, right? Okay. Okay, so now so I can construct another A map to AV, right? So now I want to tell you that use this TA to map A to the home of VV itself and try to make the yeah. So now so this A, right? For any element A, I define a linear transformation. I just map into trivial, right? Make to TA. Okay. So it's psi of A, just TA. Okay. Okay. The problem is that so you might think, or what is this vector space V? I didn't tell about V, right? But by definition, you can just choose V to be A. So if V is choose A to itself, then psi A will just be TA, right? So TA will definitely a linear transformation over this algebra. Okay, so check by yourself. So now I can check that if T is if I talk about alpha A plus beta B, econ V will be alpha A plus beta B, right? By definition, econ V is linear, so it's alpha A V plus beta B V. So this is just a alpha TA plus beta TB V, right? By definition, this AV divided basically TA, yeah. Okay, so what I'm saying is that this map, right, this map, this map, right, this map is a vector space homomorphism, right? By this, right, this is a property of homomorphism. So psi is a homomorphism of A into AB, right? Just by okay, and also you can check that if AB, easy to see if AB belongs to A, and what's TABV, right? TABV is just ABV, which is just A BV, which is just TATBV, right? So it's stupid, okay. Okay, but this tells you that TAB is basically TATB, right? Okay, so so you see now phi is a, so this phi homomorphism basically talk about vector space, right? Because it's linear. And this tell you that the phi is a ring homomorphism, right? Ring homomorphism. Okay, so combine these two. You remember that the algebra definition is basically a vector space and also a ring. So combine these two, we know that this side should be viewed as a homomorphism of algebra. Okay, so it should view as a subalgebra. Okay, so but we are not finished, right? So we need to prove is the kernel is, we need to prove is subalgebra, right? So kernel size should be 0. Okay, so this is the final check we need to prove. Okay, so kernel size 0 means what? Means that everything mapped to 0 must be 0. Okay, so so let's see, right? So if A belongs to A, so we hope to solve this psi equals 0, right? But the psi is just what, TA, right? Right, TA, right? So TA, but right, so it's just a TA. Okay, so this thing tell you that TA TA 0, right? So TA 0 means that A times V is 0, right? For every V, right? Okay, but now the key point is that I say that there is a unit element, right? So nobody can stop me, right? So I can, right? Nobody can stop me. So I can from this I can get the TEA, right? Is 0 because right, because TEA is 0 since I can times E here, right? So I can write this one as a ETA as 0. Okay. Right, but the EA is by definition, right? It's just A. Okay, so okay, so let me just write again. So I know that AB is 0, right? For all V. Okay, so now the problem is that I'm talking about, so these two object are just abstract two element times in algebra. So it's not guaranteed that AB is 0 will imply A is 0, right? Maybe there is some guy which kills everyone. But the problem is that I think the identity exists, right? So so that means EA V is 0, right? But EA is A. Right? But the problem is that the EA V is 0. Okay. Okay, so yeah, so from here that I know that E so the key idea is that, so we hope to prove what? We hope to prove that if psi 0 means that TA is 0, right? We hope to prove that if TA is 0, then we hope if TA is 0, we can prove that A is 0, right? So this is the goal. Okay. So my so A has a unit element, right? So we know that ETA is 0, right? So ETA is 0, just tell you that EA, right? EA is 0, right? Which tell you, but EA is just E, right? So A is 0. Okay, so which means that kernel phi is 0. So this is injective. So once we prove it's injective, then then we finish. Okay. Okay, so the idea is that this AVF contains lots of different algebra. So all algebra over a vector space with unit looks like a subalgebra of this. Okay, so one can talk about some results. So let's talk about lemma. So this lemma says that if A is algebra over field F with unit, and A is dimension. So I can talk about the dimension of A, right? Because A is also vector space. So let's say dimension is M over F. Then every element, so every element X belongs to A, or A belongs to A, satisfy the polynomial, satisfy some non-trivial polynomial. So non-trivial means that non-zero. So non-trivial polynomial P of X in F bracket X. Okay, so what I'm saying is that for each element A, it always contains some polynomial P such that P of A is 0. Okay, and all the field can be choose F. Okay, and this is easy, right? Because the reason is that you can take 1A squared. So let's using 1 to be identity. So 1A squared A cube, right, is M, right? So if you take up to M, then there are total M plus 1 element, right? So they must be linear independent, right? So you can find AI from 0 to M, which is 0. Okay. Okay. So yeah, so proof is done. You can take a polynomial to be AIXI. Okay, so done. Yeah. Okay, so theorem. So this theorem is also right. So from these results, right? From these results, we know that if V is a vector space, so V is a vector space over F. If V is a vector space and dimension V is N, then in particular, if I choose A to be AFV, then every matrix or every, so yeah, we haven't talked about matrix, right? But every linear transformation in A basically satisfy the non-trivial, will be a root of non-trivial polynomial, and that polynomial, right? That polynomial degree or less or equal to n squared, right? Because we proved that this guy is a vector space, which dimension is n squared, right? So by previous lemma, we proved this result. So the proof just previously, okay. Okay, and then this is the final results we will talk about in the future. Is basically Kelly-Hamilton. I think so. Kelly-Hamilton tell you that actually this polynomial degree at most. Okay, this is a highly non-trivial results. Okay, approved in the future. Okay, so. Okay, so let's talk about the invertible. So definition. So if I say T belongs to some AV, so AV is a general hum VV element. So now I'm not talking. It does not guarantee that it's a finite dimension. So has a called right invertible. It's called a right invertible. So right invertible means that you can find if there is a S belongs to AV, so you can find another S, right? Such that so I think such that right invertible, right? So I think definition should be ST equals to 1. Okay. Yeah. Yeah, I think it should be okay. So yeah, so hopefully I didn't get it wrong, right? Okay, but by the way, so if I get it wrong, then just comment. So if I remember correctly, right invertible should be ST equals 1, and yeah, so this operation means egg on T, egg on S. So you can you can cancel it from the right. Should be called it right invertible. Okay, and the left invertible means that there's a u belongs to a v such that tu is 1. Okay. By the way, this is 1, right? There's a 1 here. Okay. Okay, so it's still be example. Non every so in an infinite dimensional space, right invertible. So there is a case that t can be right invertible, but not left invertible. Okay, so this looks stupid, right? But let's talk about examples. So this means that suppose you choose TQ, right? So let's talk about it. So the vector space choosing to be, let's see, all the differentiable or infinite differentiable function from the 0, 1. Okay. So your TQ of x defined to be the integral. So let's say Q of t dtx from 1. Okay, and then you can define your s Q of x to be the derivative. Okay, so from your linear, from your calculus, right? You know that if you act on t, you first do the integration and then do the differentiation as t, right? You always get 1. This is the fundamental theorem of the calculus, right? But if you do the derivative and do the integration, you not necessarily say get q of t, right? You will get some q of 1. You will get the q of x minus q of 1, so it's not q of x. Okay. So this example is not it's very interesting, which is right invertible, but I think yeah. So what it's saying is that yeah. So what it's saying is that it's not guaranteed that it's not guaranteed in the matrix case that you can your right invertible element and left invertible is not necessarily in the infinite dimensional space. Okay, so definition. So if I say A is right and the left invertible, means that means what? Means that there exists S belongs to a V such that T, right? If I call T is a right invertible and the left invertible, I mean S there exists such as T is Ts equals to 1. Right, so this is a common. Okay, so if T is called singular, means that what? Means that the T is non-invertible. Okay, so usually we will say invertible, or basically, or there's also a common word used regular. So regular and invertible are the same in our content. So if I say T is regular invertible, means that there is an inverse such that you can multiple left and right. Okay. If T is called singular, means that T is non-invertible. Okay, stupid definition. Okay, so if 0. So if dimensional V is finite, some case, some finite space, then what I'm saying is that what? So what I'm saying is that then what? So PT belongs to AV is invertible if only if the minimum, the constant term of the minimum polynomial of T is non-zero. Okay, so remember that we proved that every finite dimensional algebra, right? Every element in that algebra must satisfy the non-trivial polynomial, right? So I can take the degree to be minimum. This is called a minimum polynomial. Okay, so this means that you can write your T to be, let's say, AKTK, AK minus 1, TK minus 1, up to A0, and such that AK should not be 0, right? So this is a minimum. Minimum means that K is a minimum, right? So you cannot find K should be greater or equal to 1. Okay, and obviously that you want to find T inverse, right? So massage this equation. Just write T as a minus A0, AK TK minus 1, AK minus 1, TK minus 2, A1, right? So this means that you just divide T. Yeah, hopefully you divide. Let's see. You just divide A minus A0. You okay. So let me just right? You change this a1, a0 here, and then you just divide this a0 minus a0. Okay, so you get this, and then you pull out k, you pull out t, Okay, so this guy, right? Basically the inverse, the inverse. Okay, so notice that if a0 is non-zero, this division can work. Nice. Okay. So this a lot of guy, this guy, just an inverse. Okay, so we prove it, right? So obviously, if t is invertible, yeah, however, if the minimum polynomial exists and a0 is non-zero, you prove that t is invertible. If t is invertible, right? So this is s, right? So what we prove is that direction is basically we prove that these directions. Let me just write here. So we prove this direction. We prove that the constant term of minimum polynomial is non-zero. Then you can shift it. You can massage this equation become this. So the rest is to prove that this direction. Okay. So if t is invertible, but let's suppose, right, t is invertible, but let's say a0 is 0. Okay, then we get z 0 equals to a1t, a2t squared. Basically it's a1 plus a2t, and up to t, right? Okay. But the problem is that now this guy, right? This guy is another minimum polynomial. So another minimum polynomial. Right? Because I can times s from this side and cancel with this t, right? So now we get another minimum polynomial with degree. Let's say k minus 1, right? So this is another minimum polynomial of the degree k minus 1. But I say that degree k is a minimum polynomial. So this guy cannot. Okay, so contradiction. Whew. Okay. It also so we get t. So what that means that one always can write t inverse as a polynomial of t. Okay, so there's another results that so I think it's also important. So if V is finite dimensional, then the t is regular. So basically it's invertible, right? So that means there exists s non-zero. So the results will imply that there exists s non-zero inside A of V, such that st equals to t, s is 0. Okay, so this means what? This means that any regular matrix can be killed by another matrix, but kill the thing kill it. The thing kill it can be non-zero, right? So what I'm saying is that so 0, right? So 0 kills everything, right? But the regular can be killed by non-zero. Okay. Okay, so proof. You're using a polynomial idea, right? So remember that we have the idea of minimum polynomial. So we get the. So let's see. We get. Oh, sorry, I'm stupid. So this is sorry. So this is singular. So if t is singular, okay. So singular. Sorry, I'm stupid. So if t is singular, then the 0 kills everything, but singular can be killed by non-zero. Okay. So singular means that no inverse, right? So that also your polynomial, minimum polynomial cannot contain a constant term. So your minimum polynomial must start with a1t, right, up to here. Okay. Okay, and then you can define s. Right? You can define s to be a1 plus a2, akt k minus 1. Okay, so check by yourself. St and ts is 0, right? And the s will be non-zero because if s non-zero, it violates minimality. Okay. Okay, 0. So this theorem tells you that if you are in a finite dimensional vector space, and if t is right invertible, then t must be left invertible. Okay, so the proving idea also use the polynomial. Okay, so now you can see that minimum polynomial is a so much powerful technique in the linear algebra, or basically finite dimensional vector space. So basically, if you not just view finite dimensional vector space as a vector space, but the so-called associative ring, and you use view as algebra, then you can have the much better results. So you can have the deeper connection. Okay, so privilege is obvious, not can we use a polynomial, right? So okay, so the idea is that so we want to prove that t is right, then t must be left. So basically, I'm saying t is right, then t must be regular. T is right invertible, you already regular. Okay. So prove. Let's see. Right. So right, but previously there is a polynomial, right? Right. So I can find such polynomial such that let's say tu is 0. Okay. So tu is 0, tu is 1, right? But if you look in your eyes, right, this u is just a polynomial, so it commute with self. So ut is 1. Okay, so u can be both inverse. Okay. Okay. And also, okay, yeah. So this is the first proof, right? So the first proof is that you just view your u as a polynomial. You can choose u to be polynomial of t, such that cancel is so the least just trivial. Okay, so another proof is that another proof is that suppose not. Okay, so what I'm saying is that suppose t is left invert or I mean okay, however, right? So suppose t has you got some u what such that t is 1, and but t is singular. So that means t is not left invertible, right? But by our theorem, if t is singular, that means you guys can find some s, right? Such a non-zero, kill itself, right? So this s can times from left, right? So you get st, u is s, right? But this guy is 0, so s is 0, contradiction. Okay, so this called it, if t is right or left singular but it's not regular, then you will you will violate the previous lemma such that there is this s non-zero such that s can kill singular. Okay. Okay, so final, I think it's up already final theorem, very close. So dimensional is finite, and t belongs to AV is singular. Okay, so up to now we can talk about. So I think from here that you guys can think t is a singular matrix. Basically, the matrix will determine 0. A singular means that you can find non-trivial vector such that the TV is 0. Okay, and proof is since we already know we can find s is non-zero, right? So yeah, I mean, so now s is non-zero, right? So so if you write as a matrix, right, it's non-zero, right? So you can find some term which you times it is non, it's this part cannot be 0, right? So you can find non-zero 1 and find corresponding 1, and this guy will be an answer for you. Okay. Okay, it's already so long. Okay, so maybe we talk next time. So next time we talk about rank and prove the various theorem. See you guys in the next video. Bye bye.